So I'm sorry to give the lecture at 9 o'clock instead of 9:30. Okay, so I just realized that I should not give third lecture. Looks like the 2 lectures is perfect. I have to made up something about the third lecture. So last 2 lectures I described this Gross-Zagier formula for the Hingham points in modular in the elliptic curve or modular abelian variety of GL2 type. I didn't say that, but you can imagine if abelian variety is modular of GL2 type, then everything is true the same. So today I'm trying to say something about what else should be true. Should be right. And so basically I want to talk about the algebraic cycles of high codimension. And unlike the point abelian variety, anything moved to the algebraic cycles, the high codimension is very hypothetical because there's so many conjectures involved that. But this conjecture somehow it's prove this conjecture is extremely hard. But to use this conjecture as assumption actually will help you to do the many important work. So sometimes, so don't feel so frustrated. So I formulate so many conjectures on Blackboard. Some of them already there for many years since Grothendieck. But if we move to the different word, like a p-adic word, sometimes you can prove some weaker version of these conjectures. And these weaker versions sometimes be useful when you get them back. So I will first talk about algebraic cycles. So I start with a variety X is projective, smooth. So I will talk about variety over Q. So this way I can assume X is connected but not geometrically connected, right? So I just be lazy. I don't want to put a number field here. So it's connected, but not necessarily geometrically connected. Like Shou-Wu varieties, for example. So the object I want to concede is so the dimension, say n is the dimension of X. So now for I between 0 and n, I have this distinguished cycle of Chou cycles. So this is the top is a free group generated by Y is a subvariety. So this is a Y. This is a integral subvariety of a codimension equals I. Modular the principal cycles. So every element of this one you can write as summation Ni Yi. Here you modular the subgroup generated by the divisor of Z of F, where Z is inside X, the integral subvariety of codimension I minus 1. This F is a rational function, right? So it's a device of that. So this group is called a Chou group of Chou cycles of codimension I. The first conjecture is probably, due to Basically, it's formulated by Bellins and Blob. I guess probably already known to Grothendieck that there's a rank. I mean, not a rank. So there's this group, CHI is finitely generated. I guess for general situation, this is one. I'll give you an example. This is actually, when I equals 1, this is nothing. So this CH1 of x is basically pick of x and the q, the rational points. So this is indeed finally generated by Mordell theorem, because this one has the two parts. Pick of x, mod of Nernst-Every group of x. Then have pick 0 of x. This is finitely generated if you take rational points. This is finitely generated, and this one is finitely generated because this one can be embedded into H2 of x of any cohomology you like. So, and basically beside this case, this conjecture is open. Even for I equals n is open. Okay. So the conjecture is open for I bigger than 1. I equals 0 is clear, as equals 0 is just a simple thing. And this group has a filtration, two-step filtration. They have a two-step. In general, I have many steps, but this one has two steps, CHI of x, 0, CHI of x. This is so-called the cycles with trivial cohomology, homologously trivial. So what does it really mean? That there is a cohomology class map with any cohomology theory you want. They're more or less equivalent. QL and x bar is x times of the q bar. So this basically is a kernel of this map, or 2i. And there have two conjectures. Okay, so the one conjecture. Okay, so let's write a name like the Ni. Grothendieck write Ci, maybe follow the Grothendieck notation. Ci of x to be the image of class. And then so we have two conjectures. They have a first conjecture, so the status conjecture. There's a Ci of x times a QL. This morphism by this class map is isomorphic to this cohomology, and x bar QL of I. And to this sense, so this one becomes weight 0 by Galois q bar of q. What? 2i. Okay, I always forget 2i. So this is the first step. And for this one, you have a morphism. So another conjecture that, so there's a, for other group, there is a morphism, just like you can embed into the Selma group. 1 of Q H2I minus 1 X bar QL of I. Then you can tensor again the QL there. Okay, let me write down this one called Abel-Jacobi map. Okay. So then you can, another conjecture. So if you tensor this by Bellinson block, I don't know is that true or not. Probably. At least the Fontaine parent real is written down very clearly. Is that the Abel-Jacobi map when tensor QL is isomorphism. So these two conjectures combined together will imply this conjecture. I mean, the top one probably, right? No, I mean the second one. But this is already finite dimensional. Okay, so I will not, so today's lecture will only focus on this part. I'll give you some trivial examples, some examples of homolog of cycles in CHI of H0. For example, one cycle, the status C of Q is a curve. Then, and the P and Q are points. C. Then you can formulate these diagonal cycles. And this C cross C. This is a P, PQ, QQ, QP. So you get alternative cycles of PP plus QQ minus PQ minus QP. It's very easy to show this cycle is homologically trivial. And not only that, you can show this cycle has Abel-Jacobi map trivial. But so far, we have no idea how to prove this cycle itself is trivial. So this is a typical CPQ. Okay, CPQ, I defined the cycle. This is inside CH2 of C cross C and 0. And the Abel-Jacobi map of CPQ is 0. But this way implies, by conjecture, CPQ is a torsion. So as far as I know, we don't know how to prove this. I'll give you two more examples. So of the cycles. So one of them is a so-called Teresa cycle. I forgot, maybe some here is right. So if you take embedding C to the Jacobian of C, then of course then you have a C inside. You also have this one has a multiplication by -1. So you also can talk about -1 of C. You take a difference of this one, this is also homologically trivial. The reason is very simple because the -1 acts all the cohomology class is a trivial, right? Cohomology class has even degree, right? So if we integrate this cycle C minus C and of any form inside, the cohomology, this was a degree, the genus G here, 2G minus 2 of the Jacobian, this must be 0, right? So it's easy to show that 0. So this cycle, let me write, this cycle also homologically trivial. And there's some work about this and when this one should be. So in general, conjecture in general should not be trivial. So finally, there's another cycle which is related to this one. Called a triple product cycle. So if you have C1, C2, C3, 3 curves, you put some points, P1 here, P2 here, P3 here. Then you can formulate a diagonal cycle. C1, C2, C3. So you have a diagonal there. No. Let me try to see. Okay, let's see. Now let's for simplicity, let's first assume all these points are the same. Just one curve. All this C here. So maybe I write in. Then you have a main diagonal. You also have many partial diagonals, the many different ones. You take these alternative sums, all these diagonals. So you have a main diagonal of delta C, right? That's a, let me write down the notation. The data, you have main diagonal X, 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 X and C. You have a lot of partial diagonals. X, XP, XPX, and PXX. Then you add back these sides, XPP, PXP, the minus PPX. Again, you can show that this cycle is homologically trivial by some reason. It's just by Kerner's formula. The reason is if this run cycle here, if you integrate this cycle with certain cohomological class, say if you have a form inside H, H22 of C, and maybe I said, for example, let's embed into the complex number of C here. Then you have a Kerner's formula. This alpha will be write down the direct sum of alpha ij, so all the different way. If you integrate this n of alpha and z, it's easy to show that one of these one will vanish under the cycles. So that's very easy to do that. So these two are typical cycles, very interesting. So you see, when you move to the cycle, like this case, it's rather easy to construct cycles, which is homologically trivial. But to show they are actually trivial is not that easy question. And for algebraic cycle, there is something. So there are two things. It's important. The first thing, there is so-called height pairing. So if we have I plus j equals n plus 1, remember this one is dimension of x. Then conjecturally, so it's still not the condition. Conjecturally, there is a height pairing hi of x 0 chi j x of 0 to real number. So conjecturally, there is a pairing. It's a narrow-tensor height pairing, so-called Bellingson-Bloch. Height pairing. And conjecturally, there is such a pairing which is non-degenerate. The construction of the cycle is not that hard, conjecturally. If you again, in modular sentence, a monodromy conjecture, a standard conjecture, then the idea is that you're giving one cycle here, one cycle there, you're trying to extend them to the integral models of this x over z, right? Then you see the integral model has a dimension n plus 1, right? So your cycle is I, codimension I, still codimension I. So codimension I cycle, codimension j cycle, and a variety of n plus 1 have the right content of dimension, so they can integral. They have intersection. The reason in modular conjecture, you don't really extend the cycle arbitrarily. The cycle with homological trivial and generic fiber, you hope you can extend this fiber, become homologically trivial, and each component of special fiber, right? And to prove this thing, you need a monodromy conjecture. And another very important remark is that in this theory, you have something called hard Lefschetz conjecture. Then you can reduce the study. Another remark is by hard Lefschetz, you can reduce the study. Reduce to the of this I, n equals 2I minus 1. Let me see, is that correct? N equals 1. Yeah, that's the case you want to study. So in this case, I will be, you can take I equals j, right? You can take I equals j. Yeah, 2I, yeah. So I equals j will be sufficient. So in this case, not only non-degenerate, in fact, I guess it's a negative 1 of I minus 1. This one should be positive definite. Okay, so this is about the cycles. They also have conjectures about the cycles relation with action. So there is the Bellingson Bloch conjecture as refined by Bloch, Cato, and Fontaine-Penrerio. So you get some certain generalization of a BSD conjecture. So roughly speaking, that So in other words, you have this rank of this cycle of x0 should be equal to order of vanishing s equals 1 of error function of this h to I minus 1 of x bar q error of I of s. Okay, so this is the weight 2i minus 1. This is a weight negative 2i, so you get negative 1, right? So it's like a theta module of a modular curve. That's weight 1, weight negative 1, right? Yeah. And of course, you have leading term identity. So we're not going to describe that, but this conjecture will help you, for example. So in particular, if in case is I, actually there is a so if I is less than, okay, let me write it in this special case. If I plus j equals n plus 1, then this thing is basically self-dual. So then this implies that this error function has a functional equation, self-dual functional equation with a sign epsilon equals plus or minus 1. So if epsilon equals minus 1, this will imply that the CHI of x0 is not 0. So again, we're in a situation that if the sign theory is negative 1, can you really construct these cycles? Before talking about that, well, so this error function is priorily defined as a absolute convergent series when real part of S is sufficiently big, right? So even talking about this conjecture, there's another conjecture by Lagrange conjecture that this one should be automorphic forms. So automorphic error functions have many other things to care about it. Okay, so this is a general philosophy or religious, if you believe, because that's, most of them is completely open. So very few things really proved. But now we want to restrict everything to Shimura varieties. Before doing Shimura variety, there's another cheaper way to construct the cycle by taking the following idea. So if you have a X is a variety, Y is a codimension 1, then you have a very cheap way to construct a cycle like that. You have a Y embedded into X cross Y diagonally. And that this one has a support this dimension n minus 1. So this is dimension 2n minus 1. This is dimension n. So that's exactly getting the situation like that, right? So the example I'm going to construct following this arithmetic Gan Gross Prasad conjecture is exactly this situation. So when I prepared my lecture, I saw that maybe they have a different way to do that. For example, if you have a morphism y phi to a curve, so it started with a map defined over Q. This is the curve. Then you can do a triple product. Y goes to y cross y cross y cross c. Take a y goes to y 5 y. This looks like another triple product. but I didn't have time. I prepared my lecture in the early morning, maybe 5 o'clock. Didn't have time to calculate this thing. How could I trivialize, homologically trivialize this cycle? Maybe it's a good exercise. Somebody want to work out this thing. So we have a cycle like that. Any good way to decompose this one to homological trivial cycles, right? I mean, to add some partial cycles. So this will be the special generalization of something like that, right? This is a 3 curve together. That's a 2 varieties plus a curve. Okay, so this is the only thing I can offer about algebraic cycles. Now I talk about, I talk about a vector space V. But we now fix, talk about V. Let me write, see what I'm going to do. I fix a K. Let me write a E. We're not going to use E as the elliptic curve. E sigma, suppose let E be either equals to Q or imaginary quadratic extension field. And I start with a V, which is over E. It's with a pairing. So when E is Q, then this is either Hermitian, the orthogonal space of type of signature n minus 2 or Hermitian. No, what is or unitary of signature of n minus 1, 1. Right, we get this in. So write G to be the unitary group. I mean the group of similitudes of the sin. U over V with the pairing. So as a reductive group. So the reductive group of a Q. If you follow Kevin's lecture very carefully yesterday, this data allow you to define a Shimura variety. So in this way, you get a Shimura variety. This will give you a Shimura variety x of k. I'm a bit stupid. So maybe I should, of dimension, let me try to make this better. Take this away. So then I know how to write a dimension. Equals n. Okay, so now I take a vector, E inside. This V is a norm, E is a positive. Take W is orthogonal complement. Right, so this will have a same signature, either n minus 1, 2, or n minus 1, 1, right? So I get a yk. Okay, this k is an open compass of group. And if you follow, I will not only, this variety is not necessarily compact. So actually, I will assume this one is compact. So you have to pay attention to the Kevin's lecture today. So I take one good compactification, some smooth compactification. So this is the Shimura variety. Corresponding to defined by the different group of H is this G of W, U of W of the parent. So then I have a bigger variety, as I said that I have a variety Y, K. I'll probably forget about K here. I mean, this K and the top K is a different K. Also, I can assume, I assume the level structure is defined by KH, because K intersects with H of QH. If I do this way, then I can embed into the YK and cross XK. So this is diagonal embedding. The radius is called Z, for example. So I give you an example. It's n equals 1. N equals 1, there's xk in both cases. Is a Shimura curve. And yk in both cases are same point. So this goes back to the situation we considered before, right? So there's a product, this and together. You just this is just the best change, right, of your Shimura curve to a certain field. So maybe this should be spec certain K, I mean a certain E, some L, you know. This L is a number field. L over Q is some number field. So this one is nothing else. It's just basically the number field. This is just a point defined by L, right? So when n equals 2, in the orthogonal case, basically you have a yk is a Shimura curve, xk is certain twist of Hilbert modular variety. Modular surface. So you are talking about the Shimura curve. This curve, a Shimura curve times the Hilbert surface, diagonally embedded there, right? In the unitary case, you have Shimura curve here, and the xk is the Picard surface. I mean, the Hilbert surface, I mean, it's a general situation. So Hilbert surface defined usually by a quadratic extension of Q, of F of Q. If F of Q is not split, it's a usual Hilbert surface. If F of Q is split, right, the product another two Shimura curves, right? So in the second situation, it equals yk. And this yk will be diagonally embedded inside here, so you get a triple product, So in the first case, in this orthogonal case, this yk and the yk cross yk has been studied by Gross and Steve. And the cycle usually called a Gross Zhang, Gross Zhang cycle. Anyway, so this is basically the situation there. And of course, then to realize the one question is, so in this case, cases, so this yk do have a canonic decomposition. Into something you should call the homology trivial cycle, yk0, and homology trivial, and something like maybe you should call it something partially Eisenstein cycle. Some other cycle is the boundary cycle, Eisenstein cycle. And in general, we don't know. In general, we don't know how to decompose this thing. Again, if you assume the Taylor's conjecture I wrote in the beginning, then you know how to decompose these cycles. Okay, so this is basically the cycle I'm doing. So now I'm trying to do the Gross-Zagier type formula. So we'll talk about arithmetic. Gan Gross Prasad. So the conjecture is proposed by Gan Gross Prasad but refined by Wu Zhang. So for reference, you have to go to his webpage. He has a couple of papers. And I also have one paper. And Dick Gross, the conference. You can go to my webpage to find out the general formulation. Okay, so unlike, you remember, when I do elliptic curve, I start with elliptic curve, I get a representation pi, right? So you will recall that if E elliptic curve, I define a pi to be the home of x to E, right? But I mean, that's just like a coincidence. In general situation, E should be replaced by a motive, right? I should have taken morphism from x to motive. And it's okay, but it's too complicated. So maybe I do it a different way. Start with a pi first. So it's equivalent. So let's start with a reduced representation of I have of G of Q, H of Q. Right? So this representation really have two parts. Like a bigger pi equals maybe small pi tensor sigma if we want. Right? Okay? So this is equivalent to the situation I'm doing before. I have a pi and a chi. Do you remember? Chi is the character. So why I have two things always combined together, but the chi is actually the character of the small group. Here is a pi of sigma. If you like, I can write a chi here. If you feel the chi always as a character. So the sigma was the character before. So I will concede this CH of the z. Remember, z equals x cross y of this is the dimension n of z, and z have all different levels. So I take all the levels, like zk, the projected limit of zk, right? I mean, for us, I just mean that this one is defined to be direct limit of this k chn of zk. Okay, I will only consider the cycle with the q coefficient. So let's write q here. Okay, so I needed to define, I start with a pi, I need to define a motive by this big pi. I don't want to define that motive, so I simply define the homomorphism from pi of chn of z of q as the linear function of g cross h. I need to have a good name. Let me write this one. Let me write a more fancy g like that. Okay. Of g of a q h. Right. And I define this in. So this is more or less is the motive I want to study, right? So you can think about it. This is it's analog of E of Q, whatever. So maybe I write on this one of model A group of pi. Just give a name. Okay? So this is the group we want to study. So the rank by BSD conjecture or Bellison-Bloch conjecture, the rank of model A of pi should be equal to order vanishing s equals 1 of L of this pi. Or maybe I normalize. I don't want to normalize that at a half, at s equals half. Okay, so I normalize this pi whose central character is a half. So this is the center. Okay, this is the conjecture following the Bellison-Bloch. If you do a refinement a little bit. So there's a cycle y. Remember, there's a yk. For all these k together is actually formulate a direct limit, a projective limit. It's different, ch and z of k. Right. So it's not a direct limit. The pullback of the cycle is not this cycle. It's a different cycle. So this actually allow you, I will not write the detail, I don't have maybe 10 minutes. This allow you to define. So this allow to define a period map, period integral. From pi to this cycle. So you get from f here, you will get the integration of f, okay, dy, whatever, over this dh and the cycles. I just symbolically write that one. Y. So this will be inside of the model value group of pi. Okay, so exactly like what we do have yesterday, we have two observations or two ingredients. The first thing is periods. Let's write on this one. The P, write H here of F. Is the P, H is in fact in the homomorphism of this big pi to C, then tensor model value group of pi is H there. H of Q hat. Right. This is nothing surprising. And again, this thing is a direct sum. It's a product of a local representation. HP of QP, P less than infinity. And then by a theorem, for many people, this thing is actually at most one-dimensional. This has dimension x equals 1 by, I hope I can remember all the people's name. Yeah, okay, so let me try to write it down. As Eisenberg, Gurevich, and she's here, right? Probably, Rallis, Schiffman. And there also has the Archimedean part given by Sun and Zhu. The first ingredient. The second ingredient is about finding a generator there. So there's the second ingredient. Second ingredient is by there is a generator. Distinguished generate of the two space tensor this H here given by, let's give a name called, we're not going to write alpha 2, given by integration matrix coefficient. So this is done by Sakalarides and Akshay. Okay. Well, so that's great. So I define a Peirce integral in this space. And for this first one, I have this distinguished generator there, right? Now it comes to the conjecture of something play the role of. So I guess now probably not conjecture anymore. So the conjecture theorem or theorem. So this is the conjecture by Gan Gross Prasad. This is probably done by Vas Puget and his student. What's his student name? About So if, let me try to see, if there, in certain situation, if the other parameter of this pi is irreducible and centralizer is trivial, if other parameter of phi of pi has a trivial centralizer in the dual group, okay, then this home is non-trivial, I guess. Then this home is non-trivial. Then there is a specific way. There is the criterion, maybe in terms of epsilon factor. For this home, this pi of c of h non-zero. Okay, so this is, I guess, probably Vas-Piaget proved the orthogonal case, right? And his student proved for the unitary case. So I guess probably right now theorem. If you combine all these things together, then you combine all this, the ingredient will give that, will give the formula. So give that, imply that exists a constant c such that for any f1 inside of pi, f2 inside of pi control gradient, that the pH of f1, pH of f2 will be equal to a constant c times this, the metric coefficient integration defined by Akshay and Yanis. Right, so before you prove anything, all this conjecture already implies there is such a constant. This is Benson-Bloch pairing. Because, okay, so what I mean that there's a pairing, multi-way group. Okay, there's a pairing between multi-way group of this representation and the multi-way group of the control gradient to the complex number. So now I will write down, this is a big conjecture. And this by Gan Gross Prasad and Wu Zhang. Is that this pH is not other than equal to 0 if not only if the derivative. Of course, I have to assume that us as a compact, in many cases, as the parameter has a trivial centralizer. There's a pi half, it's not 0. This part is actually, it's a conjecture of GGP. We can give a more precise version that, and the C here is essentially the derivative L prime pi and a half. And as a refined. Okay, now let's think about what has been proved. So the case has been proved. It's a case I stated in the last 2 days. So the n equals 1, well, this is the Gross-Zagier formula. And the complete version is proved in my book. N equals 2, in the orthogonal case, so this was treated first by, at least, by Gross and Kudler, and by my student YZZ. So we have not yet completely proved all the cases. Some special cases are done, some special cases. And the method to prove this thing, the uses this Steve's generating function is a theta series. Use Bayes representation. And the Kudler's generating function. And in other cases, I guess probably in orthogonal case n equals 2, the Bayes representation still works. But any other cases doesn't work. So in general case, when n equals 2 and bigger than 1, unitary case, we Zhang formula proposed, proposed relative trace formula. Approach. And the relative trace formula, for this starting point, you have, so in this case, inside this case, you have this arithmetic fundamental lemma. You have a smooth transform. Many things you need to check one by one. This arithmetic fundamental lemma has been proved by, this is confirmed by Wu Zhang himself, that n equals 1 and then n equals 2. So in general, still open. And well, I guess that's all the situation. All the cases we know so far. And I really hope, in the near future, when n equals 2 can be completely done. When n greater than 3, you have no idea about that. And in orthogonal case, it's completely open, even in the classical situation. And Wu Zhang just told me maybe he have some idea to do the classical thing. But for arithmetic situation, it's completely unknown. So we will see if we can do something next year. Okay, I should stop here.